Just looking at the stuff that is getting posted. Today we're going to go through kind of a part 4 of chapter 7 together. We're going to talk about quantum numbers and like how to figure them out and what's allowable and what's not allowable and what they actually do and stuff like that. Today, during your asynchronous time, there's this Explore ChemThink tutorial. And I know it's like a covalent bond tutorial, which we're not quite to bonding yet, but it actually explores a little bit of like the structure of the atom and the forces inside the structure of the atom and how to graphically portray those forces inside the atom. And I think that's all really great. It totally is talking about what we're talking about now. And anytime we can kind of evaluate things through a graph, those graphs you should really spend a couple minutes like looking at a little bit more deeply. And so this kind of gives you a visual representation of like where the graph comes from, which I really love. The other thing, it reviews naming, which is always great for us. So at the end of it, it reviews naming. So I want you to walk through that today during your asynchronous time. I'm thinking it'll probably take you about 45 minutes. And then this afternoon, we'll see how far we get in lecture and if there are some things that I can put online for you to listen to during your asynchronous time today. And then homework is just going to kind of be continuing from where you left off in your problems last night. I think the only other announcement I have or reminder that I have is during office hours today, we're going to talk about some of the post-lab stuff from Lab 2. So if you have questions on that, come during office hours today and we'll talk about it. All right. Questions, comments, concerns? Let me check the chat real fast before we get started. Feel free to ask questions out loud too.
Are we going to go over quantum spin? Because I read a little bit that.
Yes. Yeah, quantum spin is the 4th quantum number. So we're going to talk, we might get there today. We'll probably get there today. Yeah, good question. Other questions? Okay, let's get into it then. All right. Okay, so the video yesterday talked through it talked through more of the evidence behind the theory. So we could just skip the evidence behind the theory. It would probably save us like a whole day in talking if we just skipped talking about like the line spectrum and the like Rutherford model, the Bohr model, the quantum mechanical model, like Heisenberg's principle. If we just skipped all of that, it would save us time. But then I would be laying the quantum mechanical model at your feet and saying, memorize this with no context behind it. So the stuff that we've been talking to over the last couple days, there's really not a whole lot of like test questions that come off of it. But the reason we go through it, the reason we actually spend time talking about that is because I'm hoping that we're gearing you towards and kind of shaping the way you think towards being like an analytical chemist, right? Being able to analyze data and understand how it pertains to your conclusions. And so I don't want you just to memorize the quantum mechanical model. I want you to understand like why we're here and how this model is not perfect either. But hopefully chemists, maybe some of you guys are going to keep like playing with the evidence and exploring the evidence we still don't understand and kind of honing in on our quantum mechanical model. So today we're talking about the nuts and bolts of the model. starting right now, we're going to talk about what is the model, what do you need to know off of it, and how are you going to be tested off of it. So if you need like a brain reset, today's the day. Just reset your brain, take a deep breath. Let's talk about what you need to know and be able to do and be able to apply. But know that all of this is coming from like the last 3 sections of 45 minutes. All of that like led up to this point. Okay, so with that said, let's talk about the quantum mechanical model. So basically it's describing where an electron exists, and it's not talking about a specific location of the electron. It's talking about a region of probability. Okay, we are most likely to find the electron in this 3-dimensional space. So this 3-dimensional space where we are most likely to find an electron, we are going to call an orbital. If you say orbit, you are referencing the Bohr model where they thought that electrons existed on a track, like a little race car, right? If you are referencing an orbital, you are referencing this 3-dimensional space where we are likely to find the electron. There's a 90% probability that we will find the electron in this space. Okay, and this orbital is a solution from an equation. What is the equation that this orbital is the solution for? Anyone? If you said Schrodinger's equation, you are right. So when you solve Schrodinger's equation, what you get is a wave function. And the wave function describes this 3-dimensional space where we are likely to find the electron. So that's what we're talking about today. How do we describe this 3-dimensional space? And just like your address, if we want to describe where you live, we describe it by a state, a city, a street, and a numerical address, right? Just like that, we are going to describe the location of this electron using 4 different things: N, L, M sub L, and N sub S. So N is called the principal quantum number. L is called the angular momentum quantum number. M is the magnetic quantum number, and M sub S is the magnetic spin quantum number. Hopefully you have this in your notes from outlining the book already. So what we want to talk about is, what do these 4 things describe? How do we find them? And when are they allowed and not allowed? So that's what we're going to get into right now. Okay. Any questions before we talk about what these things are and how we find them and what they describe? Okay, I see a couple people in the chat saying they weren't able to get through all the video. So again, we're just this is like a fresh start right now. If you need to watch the video later to catch up on how we got to this point, that would be a good idea. But you don't necessarily need to know that to start here. Okay? Okay, what's the importance of knowing where the electrons are and how can we use that information? So that's a great question. And that kind of gets back to what we were talking about in the beginning of this chapter. Like, why do chemists care about electrons? So what does this location of the electron do? It sets us up to understand bonding, intermolecular forces, and interactions between atoms and molecules. If we understand like where the electrons are, we can understand all of these things: bonding, intermolecular forces, attraction, repulsion between molecules and atoms. And the reason we're talking about this so early in the year is because basically everything from here on out is an application of attraction between atoms and molecules. So our next, for example, our next unit is going to be solutions, also known as what are the interactions between atoms and molecules in solutions. And that's based on where the electrons are around an atom. Another one we're going to do is gases, also known as what are the attractions and repulsions between atoms and molecules when they're in the gaseous state. And all of that is based on where the electrons live around the atom. Then we're going to get into kinetics. How fast do reactions proceed? Again, based on this information. Acids and bases. So what are the attractive and repulsive forces within specifically acidic molecules and basic molecules? And so basically the rest of the year, we're talking about different applications of attraction and repulsion between different molecules. And attraction and repulsion between different molecules depends on where the electrons live around the atom. So that's why it's all important. At the end of this, we'll kind of talk a little bit about application in a small way, but basically every unit we talk about from here on out is an application of this information, which is why we're talking about it so early. Yes, SPDF orbitals come out of this. So basically, you're getting the SPDF orbitals in a much, much deeper view this year than we did last year. Last year, we kind of were like, here's what SPDF is, and we moved on. Now we're talking about that in a lot more detail. Okay, any other questions? I don't see any other questions in the chat. So I'm going to move on. Okay. So N is the principal quantum number. So N is what Bohr used to describe his orbits, his energy levels, and that's basically what we use to describe N also. So N can be any number from 1 up, but it has to be whole numbers. So you can get N equals 1, N equals 2, N equals 3, but you cannot get N equals 3.5. Okay, no decimals, only whole numbers. And what this describes is the size. So if you have an orbital that looks like a sphere, and this is your N equals 1 orbital, or N equals 1 energy level, then N equals 2 is just going to be a bigger sphere. And N equals 3 is an even bigger sphere. So N talks about the size of the orbital that you're talking about. If your orbital is a triangle, N equals 1 is a small triangle, N equals 2 is a bigger triangle, right? Also, when you're talking about the quantum number N, if you say like, I found the electron in N equals 3, we would call that an energy level. So it's kind of like the biggest, most general way you can talk about orbitals. And that will make a little more sense once we get into the other ones. L is the angular momentum energy level, and L is going to describe your shape. So we can talk about your L values as if they are a number. We can also talk about your L values as if they are a letter. So you kind of have to learn like two systems for L and how they like correspond. So L can be any number from from 0 to N minus 1. So you can't have all the possibilities of L at every single energy level. L is going to describe your shape. So it said another way, you won't find every single shape at every single energy level. It's limited based on the energy level that you have. So let's go over the shapes first, and then we'll talk about which shapes appear in which energy level. And no worries, I'm going to kind of define all of this, and then we're going to go through and practice it together. So take this information down, write it somewhere where you can refer back to it, because the very next slide, we're going to practice it. Okay. All right. So if L equals 0, that is your S shape. And from last year, hopefully you remember what the S shape is. Can anyone type into Pear Deck and tell me what the S shape is? It is a sphere. Yes, very nice. It's a sphere. Okay, L equals 1 is a P shape. What is P? Dumbbell. Yeah, so I'm going to draw it like this. Your book has a much better image of it than I do. Okay, L equals 2 is a D shape. What's D? What shape is D? Clover. Yep. So most of them look kind of like a clover. Again, this is how I'm going to draw it. Your book has better drawings. There are a couple that are not like very typical clover shapes, but we'll just ignore them for now. We'll just call it a clover. Okay, and then L equals 3 is your F shape. And what did we call the F shape last year? Crazy. Yeah, we called it crazy because they're all different. All of them are different. So the F shape is like debated right now. Like, this is what our model predicts, but is this actually the shape that of the like location where we find the electron 90% of the time? Well, we're not really sure. We're not 100% sure it's actually true. And so the F shapes, if you just know like there's something that exists, they're more complicated than SPDF because they involve more electron interactions, and they're all different, that's probably good enough to know. You really don't have to know the shape beyond that. Okay, so like I said, you can't have every shape at every level because the L is like regulated by what the N is. So I'm going to erase my little drawings over here, and let's go back to these N values. So let's look at this. If N is 1, then I can have any L from 0 to N minus 1. So that means I can have any value of L from 0 to 1 minus 1, which equals what? 0. Right. Okay, so basically, in my N equals 1 energy level, I have one possible shape, and that's L equals 0, which shape? Right, the sphere. It's the spherical shape. The only L value that is possible in this first energy level is L equals 0, which is sphere. So in the first energy level, the only possible shape is a sphere. In the second energy level, we can have anything from 0 to 2 minus 1, which is 1. Exactly. So we can have all possible L shapes from 0 to 1. Again, L must be a whole number, just like S. So your possible L's here are 0 and 1. So in the second energy level, we're actually going to find two shapes. We're going to find L equals 0, which is the sphere. And we're going to find L equals 1, which is the dumbbell. Okay, so I'm going to give you 30 seconds. Tell me what are possible shapes in the third energy level. And go. All right, and hopefully you got yourself to anything from 0 to 3 minus 1. So I could have L equals 0, L equals 1, or L equals 2. So in that third energy level, I can have a sphere, a dumbbell, and clover shapes. I will see all three shapes. So I'm not actually going to see the F shape until the fourth energy level. All right, is that making sense? Any questions on the angular momentum quantum number? Okay, so here's the deal. When we're talking about an electron, if you can tell me which N and L can describe that electron, basically what you're talking about is a suborbital. If I say, okay, well, I'm studying this one electron, and that electron is in the second energy level in the clover shape. So it's a 2p electron, right? I'll write that down. Second energy level, clover shape. My electron is a 2p electron. That 2p is talking about a suborbital. It's a little bit more specific than an energy level because the energy level would be 2. That electron lives in the second energy level, right? But it's not quite an orbital yet, and we'll talk about why that is. Okay, so let's talk about M sub L. In order to get to orbitals, we need to talk about M sub L. So M sub L, let me erase all of this. Just like L is guided by N's, M sub L is guided by L's. So for M sub L, you can have any value from negative L to positive L. Okay, so for these values, let's take these two values. I want to give you a chance to think before I walk you through it. Okay, so think, maybe talk amongst yourselves. What are possible M sub L values for L equals 0 in the second energy level? And what are possible M sub L values for L equals 1 in the second energy level? Okay, I'll give you a minute and go.
I'm still trying to understand.
have no clue, sorry.
Okay, how'd we do? I see no answers typed in to the chat or to Pear Deck. You want to take a minute and type it in so I can kind of see how you're doing? Or do you want to tell me out loud? Oh, here we go. Okay, possible M sub L's, possible magnetic quantum numbers for the two suborbitals in the second energy level. So those are the ones boxed in purple. Okay, the people that have typed into Pear Deck, you almost have it completely. The answers that I see are just missing like little pieces, but the answers you have typed in are correct. So if you are one of those people who have typed in, you're on the right track. So let me delete this over here so I can kind of expand what I'm talking about. M sub L. So this is going to describe orientation. So again, we're going to get values like 1, 2, 3, 4, 5. We're going to get whole number values. But what those values are describing is actually how many different possible orientations we can have. So if you have 3 numbers, regardless of what those 3 numbers are, it means you have 3 different orientations. So for L equals 0, for example, our sphere, our M sub L can be anything from negative L to positive L, which means negative 0 to positive 0, which doesn't give us anything really besides 0. Our possible M sub L for our sphere in the second energy level has 1 orientation value. And that makes sense. If we have a sphere, I don't know if I have any spheres in here. Okay, if I have a sphere and I turn it, it still looks the same. And I turn it, it still looks the same. And I turn it, it still looks the same, right? It doesn't matter how I turn a sphere. It's always going to look the same. So spheres have 1 orientation. Let's look at the dumbbell. Okay, so dumbbell can be anything from negative L to positive L. So negative L, 0, positive L, which means negative 1, 0, positive 1. So for my dumbbell in the second energy level, there are 3 possible orientations. And that makes sense too. If I have something that's linear like this, or maybe dumbbellish like this, I can orient it in 3 different directions. I can orient it on the X plane, the Y plane, or the Z plane. So 3 orientations for my p orbital. And this, if you have N, L, and M sub L, this describes an orbital. That's what an orbital is. So my 2px orbital looks like that. Let me do it in a different color. 2py orbital looks like that. Same shape, same size, different orientation. My 2pz orbital would come like forward and go back A Z is usually like in the plane. 2pz orbital. So same size, same shape, different orientation. And this is an orbital, one orbital. So the difference between an orbital and an energy level is the energy level contains all the shapes inside that energy level. It would contain 3 different p orbitals as well as an s orbital, right? So my second energy level would look like all of these shapes together, a 2s and 3 different 2p's, 2px, 2py, 2pz. That would be the second energy level. But if you're talking about one orbital, you're just talking about the purple, or you're just talking about the red, right? And remember last year how we talked about how when we're talking about electron configurations or orbital diagrams, and you have those little boxes that you can fill, or the little lines you can fill, each line or each little box can only hold 2 electrons. Well, that's an orbital. Each orbital can only hold 2 electrons. So the second energy level could hold 8 electrons, but the 2px orbital can only hold 2 electrons. Okay, so let's try this again. For 3D, 3D, so that's talking about, if I'm going to box it, it's talking about this one. How many different orientations or how many different magnetic quantum numbers can you have for the 3D suborbital? So work that out. I'll give you 30 seconds to work that out, and then we'll talk through it together. Type it in to Pear Deck when you have an answer. How many different orbitals can the 3D suborbital have? How many different orientations can the 3D suborbital have? Yes, 5. Yes, very good. You guys are getting this? Okay, so for 3D, okay, your L is a 2, which means you can have anything from negative L to positive L. So -2, -1, 0, 1, 2. That would be 5 different orientations, right? So these orientations get a little crazy because we can't just have X, Y, Z, right? X, Y, Z would be 3 orientations. So these orientations just get a little more complicated. I'll tell you what they are, but you don't really need to be able to predict these. So they would be like an X, Y plane. You're more describing planes here than axes. So remember, if we have a clover shape, something like this, you could have it on the XY plane. You could have it on the ZY plane. You could have it on the ZX plane. And then you can get some planes that are on diagonals. I think one of them is like the x squared minus y squared plane. The other one is like the z squared plane. So as you start talking again about graphing, when you're in like algebra 2, pre-calc, you do a lot with graphing. All of these planes are what the Schrodinger's equation answer, or the wave function, that's going to be part of their description of this picture. They're going to give you a shape, a size, and then they're also going to give you a plane on which this shape and size exist. Okay, so here's my next question. If each orbital can hold 2 electrons, how many electrons can the 3D orbitals altogether hold? How many electrons can be held in the 3D subshell? Okay, the one answer that's been typed in so far is correct. Oh, 2 answers I see that are correct. The answer is 10. Yes, if each of these orbitals can hold 2 electrons, then you have 5 orbitals, each holding 2 electrons. It can hold 10 electrons total. What about the third energy level? How many electrons can the third energy level hold as a whole? I'll give you some hints here. So you're going to have the 3s.
Ms. Martin, can you repeat the question? It was cutting out.
Yep. How many electrons can the third energy level hold total? The third energy level. So you're going to be holding the 3s, the 3p's, and all the 3d's. How many electrons total can the third energy level hold? It is just that one level, yes. So most answers I see are either correct or really, really close. Okay, the answer is 20. You should be able to hold 20 electrons total in the third energy level because the S will hold 2. There's just one shape.
Yeah, we cannot hear you very well.
Am I going in and out?
It's cutting out a lot,
It's
quite
like
a bit.
sandpaper.
Let me see if I can close some things and see if that helps. Well, we're pretty much done with class. Okay, maybe that'll help. And I'll write too. Maybe that'll help. Okay, here are your numbers. So you should be, the third energy level can hold 18 electrons total. 2 from the S. Each of the P's can hold 2, so that's 6 from the P's. And then each of the D's can hold 2. That's 10 from the D's. So 18 total. All right, quantum numbers. So quantum numbers in your book are going to be 75 through 81. But you don't have to do 75. So 77 through 81 would be the questions that we've gotten through in like asynchronous time and synchronous time. I'll type it into the chat too. There we go. Okay, I will be back, hopefully without the whale sound, for office hours. I'll type that in the chat too.